All right, in chapter 10, we're going to look at parametric equations and the polar coordinate system, and we're going to do a calculus with these different systems. And we'll start here with parametric equations. So what are parametric equations? Well, they're a way of describing a particular motion of a body or particle or whatever you're tracking using more than a single equation, where, for instance, the position of the particle that you're tracking is given in coordinates, and each coordinate is a function of a parameter, say, of time. So let's give an illustration here. So suppose you're tracking the motion of a particle or a fly or something that's moving around, and it moves in this particular way. So I think we can all agree that describing the position of this particle with y being a function of x would simply just not be possible. This is a massive breach of the vertical line test, for instance. However, by introducing the concept of parametric equations, we could look at a point on this curve and say it's xy. Well, we could define x as a function of t and y as a completely separate function of t. And this is called parametric equations. So now you would give a specific t value, and f of t would simply track that particle's x coordinate, and g of t independently tracks that particle's y coordinate. So parametric equations occur in pairs like this. X equals a function of t, y equals a function of t. Although in higher dimensions, you could have more parametric equations. If you were, say, tracking a particle's motion through three-dimensional space, then you would have z equals some other function of t. In this context, we refer to t as the parameter. All right, so let's get right into an example here of some parametric equations. Okay, so here we are given a set of parametric equations, and we're asked to sketch the curve defined by these guys. Okay, so yeah, why don't we just make a table of values? So normally, a table of values has you choosing, various x values and then calculating corresponding y values. Here, the independent variable is the parameter t, and both x and y are dependent variables. So we're going to have three columns in our table of values. T, the independent variable, and then x and y. So let's choose some t values. And what we're going to do is plug t equal these values, say -2, into the x equation and into the y equation, and we will write our outputs in the corresponding entries in this table. So for instance, when t is equal to -2, we can see that -2 squared, which is 4, minus 2 times -2, which is 4 plus 4, so that is x equal 8. And in the case for y, when t is -2, we have y equal -2 plus 1, which is -1. So at the occasion, when t is -2, we can think of t as time. So at time equal to -2, the particle that we're tracking is at location 8, -1. So we can actually sketch this point. So let's draw some axes and do that. So at t equal -2, our point is at 8, -1, so right here. Okay, so now at t equal -1, We plug into the x equation and we'll get negative 1 squared is positive 1 minus 2 times negative 1, so positive 1 plus 2, that is equal to positive 3. And plugging negative 1 into the y equation, we'll get negative 1 plus 1, which is 0. So at t equal negative 1, our particle is at the point 3, 0. All right, so let's quickly fill in the rest of these. And let's plot these points. At t is equal to 0, we know that the particle is at the point 0, 1. And at t equal 1, the particle's at negative 1, 2. And at t equal 2, the particle's at 0, 3. So it seems to have turned a corner. Okay, and you can see that there's perhaps a parabolic shape sort of emerging here. And we would get more of the story if we plugged in more t values. So let's actually plug in t equal 3 and t equal 4 as well. Okay, so at t equal 3, the particle is at the x-coordinate 3, y-coordinate 4. So the point 3, 4. And at t equal 4, the particle's at 8, 5. So indeed, we are getting this parabolic shape. And as it turns out, we're going to see that this is actually a parabola. Now, it's helpful when sketching parametric equations to indicate the direction of increasing t on your curve. So I usually just draw a couple of arrows, so no matter where you're looking on the graph, it's fairly obvious which way the action is moving. Okay, now in many cases, we are going to be able to do something called eliminating the parameter, which is converting the set of parametric equations to a single Cartesian equation in terms of x and y. Now, a Cartesian equation is just the equation in terms of x and y that we know and love and we're used to. So as this is a curve with a fairly regular pattern, in fact, we're conjecturing that it's parabolic, we ought to be able to eliminate the parameter and have a nice recognizable equation in terms of x and y. So let's look into doing that. So eliminating the parameter means isolating t in one of the equations and then substituting that into the other equation. So what you have is a single equation with x and y. So let's write down the equations as we left them. So pick one of the equations to isolate t in, and I think the choice is obvious here. Let's solve for t in the second equation. T is y minus 1. And then we're going to substitute y minus 1 for t in the other equation. So here's the other equation, and substituting y minus 1 for t, we get this form here. So let's FOIL the right-hand side. And let's complete the square to get this into standard form. So what we would want is a plus 4 here. So we'll have to subtract 1 to keep it balanced. And so we get x is equal to y minus 2 squared minus 1. So again, this here is called the Cartesian equation. It's the type of equation we've been working with pretty much all of our mathematical lives, but now we need to refer to it as something to distinguish it from a set of parametric equations, and then a little bit down the road from polar equations. And looking at this, recognizing that this is indeed a conic section in standard form, this is a horizontal parabola, and it has a vertex of negative 1, 2. And this coincides with our graph. Okay, let's see how we can sketch parametric curves on Desmos. So on Desmos, to sketch a parametric set of curves, you actually just enter it as a coordinate like x, y, except this doesn't know what to do with that. So instead of literally writing x and y in there, we put the equation for x and y in terms of t. So for instance, here we have x equal t squared minus 2t. Now it doesn't know yet that we're trying to write a parametric equation, so it's going to offer to add a slider for t. We don't want to take that option. We're going to go comma, and now we'll put in the function for y, which was t plus 1. And we can close the parentheses. At this point, Desmos realizes we're trying to enter a set of parametric functions, so it gives us bounds for t. And let's just put in what we had, which was -2 to 4. And you can see there is our parabola that we found. Let's put in also our Cartesian equation and see if it overlaps. So x equals parenthesis y minus 2 close parenthesis squared minus 1. And yes, you can see that it overlaps. All right, so here we're going to sketch a curve and then eliminate the parameter. We're given bounds on t. So that means this is just going to be some segment of a curve, not an infinite long curve in both directions like the last one. All right, well, let's make a table of values. So because we're given specific bounds, well, let's just put those in directly. -2, -1, 0, 1, 2, and 3. Okay, so plugging those t values into the set of parametric equations will give the following results. So these are the coordinates that we need to plot. So let's go do that. Okay, so let's plot these points, -4, -1. And as you plot the points, try to imagine what curve is emerging here. The next point is -1, +1. And then followed by 2, 3. Followed by 5, 5. It looks like perhaps a straight line, but we can't say for sure without plugging in the other points, because maybe it's a straight line and then suddenly like a dinosaur. So I don't know, let's plug in those last couple points. The next point is 8, 7, and followed by 11, 9. So if you were Team T-Rex here, I'm sorry, this is just a straight line. Now we've connected this with a straight line, and let's show the direction of increasing t. But be careful not to extend the line outside of the initial and the last point, because we were given this bound of t being between -2 and +3. So it's just the line segment. Okay, that was very interesting. Let's do part B, eliminate the parameter. Okay, so to do that, we're going to isolate t in one of the equations. Let's just isolate t in the first equation. So we can see from the first equation that t is equal to x minus 2 over 3. And therefore, if we take x minus 2 over 3 and plug it in to t directly in the other equation, we're going to get our Cartesian equation. So that'll be 2 times x minus 2 over 3 plus 3. And indeed, you may recognize that this is the form of a straight line, right? This is just y equals mx plus b. In fact, if we clean it up, we're going to get y equals 2/3 x and then minus 4/3 plus 3. That would be 5/3 here. Now, we are not quite finished eliminating the parameter, because this equation doesn't faithfully represent this particular system, as we have not incorporated the restriction. So how do we transfer this restriction to x values? Well, we just look at this function and say what's the absolute min value and the absolute max value of this function over this interval of -2 to 3. And since this is a monotonic function, meaning it's increasing or decreasing, all you have to do is plug the bounds of t into this function and you'll get immediately the restriction on x. For instance, when t is equal to -2, we get x being 3 times -2, which is -6, plus 2 is -4. And when t is equal to 3, we plug that in, we get 3 times 3 is 9, 9 plus 2 is 11. So we have this bounds here on x, -4 to 11. Of course, that's represented on our graph, -4 to 11. Okay, so here we're going to determine what curve is represented by these different sets of parametric equations. And we're going to do this just by eliminating the parameter. So let's start with part A. All right, now in the examples so far, to eliminate the parameter, what we've been doing is isolating t in one of these equations and then substituting into the other. And when you have trigonometry, there can be a few things that go wrong with that process. So let's be very, very careful. For instance, if we were to let t equal inverse cosine of x, which would be, I think, a good natural instinct here, let's keep in mind that this doesn't faithfully represent all the t values in the range that we're given here. For instance, we understand that the inverse cosine function outputs t values in only this range, 0 to pi, right? The first two quadrants. So we would have to make some adaptations to manage the second half of our t values from pi to 2 pi. Even worse would be if we'd isolated the t on this side, because we'd get t is equal to inverse sine of y. And now the bounds of t from the inverse sine function we understand to be -pi over 2 to +pi over 2. And half of these t values aren't even in the range of t values that we care about. So again, it's not to say that you couldn't work your way through this and make adaptations so that everything worked, but this is not the approach we should take. So when you have a bunch of trigonometry like this, just ask yourself what trigonometric identity relates these two equations, and that pretty much is going to produce your Cartesian equation. So we know, of course, that cosine squared of an angle plus sine squared of the same angle is equal to 1. Well, this is perfect, because cosine squared is simply x squared, and sine squared is y squared. So we get x squared plus y squared equals 1, and we recognize that as the unit circle. In fact, the question merely asked what curve is represented here, so the answer is the unit circle centered at the origin. Okay, this makes a lot of sense, because we know that any point on the unit circle is given literally by cosine of an angle, comma, sine of the angle, right? That's a thing that we learned in trigonometry. So here, the angle is t, and our bounds are t starting at 0, ending at 2 pi, so this is exactly one lap around the unit circle. All right, let's do part B now. So again, for part B, we're going to eliminate the parameter. Okay, so yeah, this is a bunch of trigonometry. So can we think of an identity that relates this form and this form? And don't be fooled by the double angle in there. That's pretty irrelevant. We can use the same Pythagorean identity we used a moment ago, which is cosine squared of stuff plus sine squared of exactly the same stuff is equal to 1. Well, there's x squared, there's y squared. So we have x squared plus y squared equals 1. Okay, so unit circle again. Okay, so what's the deal with the 2? How is that affecting things? So let's suppose we have our regular cosine and sine of t here. So there's our t. Now, if we double the angle t, that'll get us right here. And this point would be cosine and sine of that angle, which is cosine of 2t, comma, sine of 2t. So you can see that they both trace out the unit circle centered at the origin, but the second example here laps it twice. This seems like a good one to look at on Desmos. All right, so we have here the graph of the first set of parametric equations, cosine, sine. And of course, if we turn on the second one, we're going to see we get the same unit circle. So just overlaps it. All right, so now we're going to see a really cool feature of Desmos because we've changed the endpoint from 2 pi to a, and then Desmos added a slider for a, which is currently set to 0. So as we slide the slider to the right, what we should see is the graph of part A's parametric functions, so cosine, comma, sine, actually generating. And it should make exactly one lap of the unit circle. So as we slide the slider, we've done one lap of the unit circle. And now A is set to 2 pi. Okay, now we're all set to do this again, but this time with part B. So that was cosine of 2t and sine of 2t. And we expect this thing to go around the unit circle twice. So let's see. All right, so A is currently set to pi, and we've gone around already a whole time, and we're only halfway through our trek, so it's going to go a second time. Watch that blue particle moving around a second time. There we are. All right, and I've just turned everything on, so let's do one more run of this. We're going to go from 0 to 2 pi, and we'll see the blue particle running twice and the black particle running only a single time. So there we are. Math is neat. All right, so again, we're given a set of parametric equations here, and we are asked to sketch the curve. So yeah, let's just make a table of values. Now, we understand that the range of the sine and cosine functions are -1 to +1 each. So the entire graph is going to live in this space right here. All right, and let's also choose t values that are really nice for trigonometry. So these are angles that should be like pi over stuff, right? We don't just want to let t equal 7, right? That's a bad idea. So let's start with t equals 0 and see what our corresponding x and y values are. So cosine of 0 is 1, and sine of 0 is 0. So our first point at t equals 0 is the point 1, 0, which is right here. So now let's plug in pi over 4. So when t is pi over 4, we get cosine of pi over 4, which is read 2 over 2. That's about 0.7. And sine of 2 times pi over 4, which is sine of pi over 2, that's 1. So this is going to be 0.707, comma 1. So that's about here. Next, let's let t be pi over 2. Cosine of pi over 2 is 0. And sine of 2 times pi over 2, which is pi, sine of pi is also 0. So we're now at the origin. Okay. So next, let's try 3 pi over 4. cosine of 3 pi over 4 is negative rad 2 over 2. And sine of double 3 pi over 4, which is 3 pi over 2, that would be negative 1. So we're now at negative root 2 over 2, it's about 0.7, and negative 1. Okay, let's plug in t equals pi. So cosine of pi is negative 1, and sine of 2 pi is 0. So we're at the point negative 1, 0. So let's take a look at our path here. We started at the point 1, 0, and then we kind of went up and down like this, and then back up like that. All right, let's keep going. Next would be 5 pi over 4. So cosine of 5 pi over 4 is negative rad 2 over 2, and sine of 5 pi over 2 is positive 1. So we're now at negative rad 2 over 2, comma 1. So that's up here. Okay, the next would be 3 pi over 2. Cosine of 3 pi over 2 is 0, and sine of double that, sine of 3 pi is 0. So we're back to the origin. Okay, we'll just do a couple more. 7 pi over 4. Cosine of 7 pi over 4 is positive rad 2 over 2, and sine of 7 pi over 2 is negative 1. So that's positive rad 2 over 2, negative 1, that would be right here. And finally, let's put 2 pi in. Cosine of 2 pi is 1, and sine of 4 pi is 0, so we're back to 1, 0. And you probably could have predicted that at this point. So let's put in our direction of increasing t. And what we have is this sort of figure 8 shape, and it's called a lemniscate. What if we actually endeavored to eliminate the parameter? Like, what would we get? Well, let's see. So again, we're going to avoid, using inverse trig functions. Sometimes you have no choice, but we're going to avoid that. Let's think of an identity that relates these two equations. So we have sine of 2t and we have cosine of t. Well, we know that sine of 2t is 2 times sine of t cosine of t. We can see that sine of 2t is y, and of course we have a 2. So now we just have to work out what sine of t and cosine of t are. Well, cosine of t is simply x, right? What's sine of t? Well, sine of t is plus or minus the square root of 1 minus cosine squared of t. So that would be like writing y here as plus or minus 2x radical 1 minus cosine, which is x squared. So it's this plus or minus here that's creating the breach in the vertical line test. We can resolve this somewhat and have a satisfactory Cartesian equation if we just squared both sides. So we get y squared is equal to 4x squared times 1 minus x squared. All right, let's go to Desmos and see if this makes any sense at all. Okay, so there's our lemniscate, cosine t comma sine 2t. Let's put in the Cartesian equation that we found. Hooray! It works. All right, for our remaining examples, we're just going to simply practice eliminating the parameter to find a Cartesian equation. So here we have this particular set, and let's go in and do this. So of course, one thing you can do always is literally solve for t in one of the equations and then substitute into the other. So like we could solve for t here, and we get that t is equal to ln of x. And then therefore, y is equal to e to the negative 2t. means that y is equal to e to the negative 2 ln of x. And you can see that that means that y is equal to e to the ln of x to the negative 2. And now the e and the ln cancel. So you just get y equals x to the negative 2, or 1 over x squared is rather nice. So there we are. Another approach could be to start with y equal e to the negative 2t and just take advantage of the fact that the equation for x and y are so similar to each other that we could probably get this to work without actually isolating t and using logs. So we could say, for instance, that y is equal to 1 over e to the t squared. That's what e to the negative 2t means. But e to the t is just x. So y is equal to 1 over x squared. And there we are, again, with the same answer, of course. Okay, in this one here, we could perhaps solve for t in the first equation and get t is equal to the cube root of x. And then substituting into the other equation, which is y equal ln t, we get y equal ln of the cube root of x. And of course, we could also write this as 1/3 ln of x and be on our merry ways. What would this look like if we isolated t over here first? So if you say, well, from the second equation, we could write t is equal to e to the y. And then substituting that into the first equation, we'd get x is equal to t cubed. That's e to the y cubed, which is e to the 3y. So that's also a perfectly valid answer, and it's equivalent to this other answer. So just keep in mind that you might work it out one way and someone else might work it out a different way, and you have different looking answers, but of course these are really the same thing. Okay, everyone's favorite, cosh and sinh. So again, you could isolate t in one of them and you'll get an inverse cosh or an inverse sinh. And in fact, you can write their inverses in terms of logarithms. So this is all very doable from an algebraic standpoint. However, there is a well-known identity relating these two hyperbolic functions, and that is simply this one. Cosh squared minus sinh squared is equal to 1. So, awesome. That's x squared. That's y squared. And 1 is 1, of course. So we simply have x squared minus y squared equals 1, which you may recognize from pre-calculus as the unit hyperbola. And that gives some credibility to the naming of these functions as hyperbolic functions.